Hello everyone. Can you hear me? Can one of you drop a hi in the chat? Um, and, can you see my screen? Okay, thank you. So, okay, let's start. I hope the audio is better now. So, I guess there are around 13 students. Hoping a few more will join. This is a pretty large class. So, as I think has been informed to all of you, there are three PMRF PAs in the course. I am Soumyadeep. I am a PhD student at IIT Kanpur, and I am a Prime Minister's research member. So there are three of us, and we have three sessions for this course. So mine will be at this time, Sunday 3 to 5 p.m. starting this week, every week for 12 weeks. And so will be for the other students. And what we will do, at least what we are planning to do is, we will help you clear your doubts and solve some typical problems that that are related to the content that has been covered in the previous week. So I would first like to hear any doubts that you might have. Any questions? Uh, if you've gone through the lectures in the first week, like have you gone through the lectures of the first week? You can type yes or no in the chat as you wish, as it applies to you. Okay, thank you. So this week's content is fairly introductory. It is more of a revision of older concepts like digital signal processing and things like that. And I'm trying to get rid of this weird. This just bear me for a minute. So I'm connected with my tablet on this other device, but I want to get rid of this. Let's see if I can do it. Doesn't seem like it. Okay, this is better. This is better. Okay. So fine. So this week's lecture is easy to catch up with. I would say, even if you've not seen it, it's fine. It's very basic. From the next week onwards, the topics get a lot more involved, and yeah, so then the course progresses quite rapidly after that. So anyway, again, I'd like to ask again any doubts that you have with the lecture? Anything you would like me to clarify? If not, then I'll try solving some typical questions. But I would like this. I would prefer this this should be an interactive session because otherwise it's like a regular classroom, and if you're taking an NPTEL course, I hope you are interested in the course. It's not a mandatory requirement, and so I would encourage you to ask doubts. even if you've posted on the forum there, we haven't, the process is started, we haven't kept. There is another TA who is looking at the doubts on the forum and making the content available. So he's trying to get back to all of the doubts that are asked on the forum. But you can ask the same doubts here. And I can see if I can answer it in some way. Okay. Some more students joining in. So I'll wait till 3:20, I guess. Some students are joining in, and meanwhile, all of you can maybe just browse through the lectures and see if there is something that you would like me to cover. Okay, I think this is probably nobody, no more people are joining. Fine. So if there are no doubts from you, I'll start by solving some questions, and feel free to interrupt or clarify things with me if you want. So okay. So here's maybe the first question on the topic on the topics covered here. So let's say you are given some signal x of t equal to 1 plus cosine of 2 by f1 t plus sine of 2 by f2 t, right? So this is a signal that you are given, right? So you are asked to determine this is a signal. It's called a continuous time signal, right? Basic. This is not wireless communication also. This is the reflector of basic signal processing. And so this is a continuous time signal. And so you have to discretize it using certain sampler. And so if you might remember that there is something from the Nyquist rate, right? For digital signal processing, FS. So the Nyquist rate is the minimum frequency at which you can safely sample this signal. So this is determined to avoid something which is known as aliasing, that is to prevent multiple copies of the same signal from mixing and distorting each other. So you need to sample it at a minimum Nyquist rate. And so you have to determine the value of for this signal. So what is so the question is, okay, to be clear, I will be sharing these notes, whatever I'm writing down. I'll be making a PDF of it, and I'll be sharing it in a drive link. I have not made the drive link yet. I'll make it soon after this session ends, and it will be added to the shared resources and shared with you. So in the same way that you got access to this link, this meeting link, you will also get access to a drive link where I'll be uploading whatever notes that I make during the session or some other references, anything that is relevant, anything that I find can be of use help for you. And as you know, most likely that this lecture is being recorded, and I will be uploading the recording on YouTube shortly after the session, and the video will be available. So you don't need to really take down notes. It's fine. You just need to follow, and everything will be available online for you. Somebody asked a question, I think, or no? Okay. Okay, and also another thing, like all of the 3 sessions that we'll have, until and unless we inform otherwise, all of our sessions will roughly have identical content. So you can join any of them, unless we announce otherwise. You can join any of them, and according to your convenience, your schedule. I've kept mine on a Sunday. It's convenient for me. So, the others have other days, so it's up to you. Anyway, with that done, so I have to find the value of fs for x of t. So that is the question. So we need to really write the Fourier transform of x of t, right? Or at least, if not the Fourier transform, formally, we should identify what are the signals over here, right? So x of t, and I'm just solving the problem right now. So x of t has three parts. Let me write x of t again. 1 plus cosine 2 pi f1t, some frequency f1, plus sine of 2 pi f2. Right? Now f1 and f2 are not necessarily equal. So they can be different frequencies. Right. So here's the thing. For this, so it is a sum of signals with different frequencies, if you notice. For this signal, this is a DC signal. A DC signal has a frequency of anybody on the, what's the frequency of a DC signal? Any answers?
Zero frequency. Zero.
Zero. Yes, exactly. 0 hertz. 0 hertz. Right. What is the frequency of this cosine signal? Yeah, the previous answer is correct. It's 0 hertz.
F1.
Frequency f1 hertz. Right. And this sine signal?
F2.
F2 hertz. Right. And so, what does the Nyquist criterion tell us? That Fs has to be two times the bandwidth, right? The maximum bandwidth possible, the maximum. So if let's say if I have to draw a Fourier diagram of this, so I'll have one impulse at 0 hertz, another impulse will be at, it's actually plus minus f1 here. If you remember, cos 2 pi f1 is e to the power j 2 pi f1t plus e to the power minus j 2 pi f1t by 2, right? We all know this. So there are two frequencies, plus minus f1 hertz. And here also there are two frequencies, plus minus f2 hertz. So how does this signal look like in frequency domain? And these are things that you have to be comfortable with in general. So if I convert this to Fourier, even without doing any math, very simply I can see that there is one pulse at 0, and then there are two pulses, let's say 0.5 of 0.5 value, two pulses at plus f1 and minus f1, and two pulses at plus f2 and minus f2, right? And this is for the case when f2 greater than f1. If f2 is less than f1, then you can just change the positions. So what is the bandwidth? What is the total bandwidth of this signal? Like, what is the maximum spread in frequency of this signal around 0? Okay, somebody has written the answer. It's f2, I think. Right? 1 second. It is f2 in this diagram. Yes, it is f2 in this diagram. But so that is because f2 is greater than f1. Otherwise, if f1 greater than f2, then what will be the answer? That will be f1, right? So this will basically be 2 times max of f1 comma f2. Does this make sense? Because I don't know the values. Like if I put particular values, then I will know. But essentially, we'll have 2 times max of f1 comma f2. Is this any doubts with this or something you want to do? In this diagram, I've drawn it like f2 is greater than f1. Otherwise, it would be the other way, right? f2 will come here, f1 will come there. Is this clear? Okay. Okay. So this will be the answer in this kind of problems. Right? Is this clear? Any doubts? Otherwise, I will move on. So again, just to revise, Nyquist rate is 2 times the one-sided bandwidth. That's how they write it, right? 2 times the one-sided bandwidth. And so you just have to imagine the signal or have an idea of what the signal is like, and then calculate this. Okay, good. So let's try another question based on the same concept. Uh, so I've been given that I have a signal, some, okay, I have some, let's say, some kind of signal. So sound, let's say sound wave, right? Audio signal. And the bandwidth is one-sided bandwidth is given to be 12 is given to be, let's say, 100 like 10 kilohertz, okay, right? 10 kilohertz bandwidth on one side, right? So it kind of, if I have to draw this, it probably, if we assume that it is baseband, it will look somewhat like this, 0, 10, minus 1, right? It's 10K of it in the kilowatt. So that is X, F given F. So, so we are told that sampling is at Nyquist rate. Sampling is at Nyquist rate, and then on top of it, there is a quantization of the output samples. Yes, sampling rate. Yeah, the answer is correct. I'll complete the question and then I'll ask the. I'll complete the question and then you can answer. You are right. Single the sampling rate is 20 kilohertz. So the quantization is, let's say, quantization is 4 bits per sample, right? So after every sample is quantized into 4 bits. So question is data rate of the data rate of the stream, audio stream. The answer is you're numerically correct, but your unit is wrong. Single. I'll come to it. So then we know the Nyquist rate. Nyquist rate will be sampling frequency will be 2 times the one-sided bandwidth, which is 10 kilohertz. So this answer is 20 kilohertz. This much is known. Or by hertz, hertz is anyway samples per second. So this is 20 kilo samples per second, right? And then for every sample, you are transmitting 4 bits of information. So you will multiply the quantization to this. So your bit rate R will be 4 times. So if you like write the unit properly, 4 bits per sample times 20K samples, sample per second. So sample can cancel roughly. So what you will have is 80K bits per second, 80K BPS. And yeah, finally the answer is that. So this is the data rate of this. Something like that. So this kind of questions is pretty common. Okay. Any doubts? I'll wait till. Okay, if there are no doubts, I'll move on. No. Okay. Okay. So now we already talked about quantization, and so there are various ways of encoding data, right? Various modulation schemes that are used. So, and the task of these modulation schemes is to. So in the previous question, we got the data rate in terms of bits per second, kbps. So we have a stream of bits. Now to send it over the communication channel, we need to encode it into, modulate it into symbols. And so we use various constellations like BPSK, like BPSK or QPSK or 16 QAM. So those will encode the bits into symbols and then actually send the symbols in the air over the radio interface. Um, so let's say you have 16 quadrature amplitude modulation. This is what you're using. So let's say so my question is 16 QAM symbols contains dash bits. So you have to fill in the blank, something like that. So any answers?
4 bits.
4 bits. Yes, you're right. 4 bits. And yeah, that's pretty simple. 16 QAM. So we know how it looks like. There are like 1 second. So there are 4 quadrants here, 4 here, 4 here, 4 here. So there are 16 symbols, 16 constellation points, and each of them we can denote them using 4 bits to indicate. If we use an indexing scheme, with 4 bits we can cover all 16 symbols. So this contains 4 bits. Right. Now, okay. So if this is clear, we can do some more algebra like this. Let's say there is some kind of, let me call it something like modified BPSK, right? Modified BPSK, where I have 2 symbols. So I have like -1 and 1 with 0 in between. So this is how the constellation looks like. But then they have different probabilities. In normal BPSK, we assume that the probability of both symbols is half, right? Instead of this, let's say I have something like 1/3 and 2/3 probability. So with 2/3 probability, I'll encounter 1 bit, and 1/3 probability is that I'll encode it into a -1 bit, something like that. So what can be the average average symbol energy, let's say? I think no, I've made a mistake in the question. One second. I shouldn't write it this way. Modified VPSK, let's say instead of -1 and 1, you have something like we don't have 0 as the center anymore. Let's say this is something like 0 and 1. 0 and 1 are probability. Or you can call it on-off scheme. Off stands for 0, and this is for 1. I shouldn't, in a constellation, we'll always have equal probability. But I was more interested in the math of it. So what will be the average symbol energy for this constellation diagram? Okay, so what's the energy of 0? 0 of the 0 bit. It is 0. And the energy of the 1 bit is 1. And so I just need to, because this is mod 1 square is 1, mod 0 square is 0. And so I just need to take the expectation and multiply the probability distribution. So this will be half times 0, half times 0 plus half times 1, right? So this will be half. Some questions like this you can expect. You're given some arbitrary constellation and you have to find out what is the average energy of the symbol. Okay. Okay, units of average symbol energy. Well, usually, like in toy problems like this, you're never asked for the units. Well, the unit of energy is joule in general. So I can write it as half joule. But it's mostly a mathematical exercise here. So unit should be joule. SI units, basically, or millijoule, whatever. Yeah. But yeah, that's it. Any questions? Okay. Okay, so I've been asked any example of 16 QAM. Well, 16 QAM is exactly like this, as I showed. So I can just draw it more neatly if you want. There is no, like, 16 QAM is defined just the way I drew it. My drawing might not be great, but I'm trying. So let's say 0. This is, let's say, at 1 unit. This is at 3 units. This is -1. This is -3. This is 1. This is 3. This is -1. This is -3. So, okay. So if I get your question, okay, for 16 QAM, how you will find average symbol energy? The method is the same, right? There is no difference. Like whatever I showed in the toy example here, it's the same method. So you know that all of the symbols are equally probable, right? So there are 16 symbols here. 1, 2, 3, 4, 5, 6, 7, 8. So 16 symbols. So energy of symbol, if you, again, I use this notation because it makes the mathematics clear. So what is expectation of a quantity? Expectation of a quantity is summation of probability times the value, right? Overall over all of the entities. That's the general definition of expectation, right? And so since they are all equally probable, so Pi is equal to 1 by 16 for all I. This is clear, right? There are 16 samples. So then we have this thing, 1 by 16 times I summation Si square. Now, all you have to do is, in this notation, in this diagram, this is a 2D coordinate system, right? It is, to be accurate, this is essentially real axis. This is imaginary axis. So this is complex number mathematics that we are doing. And so the energy of this mod Si square is nothing but the distance of these points from the origin. So you have to find out the distance of these points from the origin. And so yeah, that's all right. Mod Si square is nothing but mod Di square. So whatever is the distance, you can calculate, right? This will be root over 1 square plus 1 square. So it will be root 2. And so essentially, if you see coordinate wise, distance will be root over xi square plus yi square, right? That is how coordinate system works. And so all you need to do is do Di square. So I can simply replace this as 1 by 16 summation I. Di square will be xi square plus yi square. You can just put xi, yi and find out the answer. That's all. For all 16 symbols. Is that clear? Or like, I don't want to solve it completely. You can do the mathematics, but I hope the idea is clear. Okay. Okay, good. Okay, let's look at a little bit more of visualization. So in communication systems, we have various kinds of signals, right? We have baseband, passband, real signals, complex signals. So by looking at a signal, you should be able to identify what kind of signal it is, right? Whether it's baseband, passband, or real complex. So let's see. I have some signal, let's say X, F, and it looks like this, right? This is, let's say, a real part of the signal in Fourier domain. And I have imaginary part of the same signal, X, F. I'm just writing real and imaginary part separate. And the imaginary part looks somewhat like, let's see this. It's exactly the same, like, of course, this is plus B minus B plus B minus B. And B is the one side of the volume. So this is how the magnitude, the Fourier transform, the magnitude response of a signal looks like. And so the question is, there are two parts, let's say. First part is, whether it's baseband signal or passband signal. And the second part is whether it is a real valued signal or complex. by real or complex, I intend to mean we need to find out if x of t is real or complex, right? We know x of f is complex. There is a real and imaginary part, but the real signal, that is the time domain signal that has been converted into frequency domain, we want to find out if that is real or complex. So how do we figure that? Okay. Yes, Mr. Singhal. It is baseband, and so the answer to the first part is correct. It is baseband, uh, because as you can see that the signal is bounded around zero. So within a small frequency around zero. So that means it is something that has probably gone through a low pass filter. So it will pass. It is the product of a low pass filter, and so it is baseband, right? And 1 second. And so the second part, whether it's real or complex, I got an answer from K. Vivla. Uh, and the answer is I got the answer complex. I don't think that's correct. This is a real signal. And the reason is we have this property of Fourier transform that if so let's look at x of f, right? X of f. Instead of x of f, if I have to draw the diagrams for x of minus f, right? How will it look like? So we can see that the real part x of f, x of minus f, let's say. So what you do when you do x of minus f is you just rotate, you just take a mirror at the origin and just rotate it around the origin, right? So, but this is symmetric, so nothing will change. So this will still look the same. And the imaginary part, the answer for this is real. The imaginary part of x of minus f will, however, it will okay, I got a query, but I'll Mr. Ravikiran, I'll answer you a little later. Let me finish this discussion first. So this imaginary part of x of minus f, if you just again visualize it, if you just rotate it around zero, then this will look like this thing, right? Okay. This will look like just the opposite. That's the minus. So now, so x of minus f looks like this. Now, if you take complex conjugate of this, x star of minus f, then if you remember that for complex numbers, conjugate means that a plus ib becomes a minus ib, right? So then essentially the real part stays the same, the imaginary part flips sign. So you will just take a mirror and reflect it along the x-axis. And so if I change this to x star minus f, what will happen is I'll again get the sorry, 1 second. I'll again get the original signal back, as you can see. So what I have is x star of minus f is equal to x of f, right? Because these two are exactly the same. This and this are exactly the same. And so So this is a property that if the signal x of t is real, then we have x of f to be conjugate symmetric. And this is actually bidirectional implication. If you remember, this property is known as conjugate symmetric. That if you take the conjugate of the signal with negative frequency, and it will be same as original signal. So now that we have determined that x of f is conjugate symmetric, we can conclude that the original time domain signal x of t is small x of t is real. I am in general using capital X for frequency domain and small notations for time domain, as is the usual convention. Is this clear? Okay. So the answer for this is a real baseband signal. That's the answer. Fine. Baseband. Okay. Now, Mr. Ravikiran, question number 3, it is as per my notation, is 10 correct? I need to solve and see. It is solve and see. I believe this is your assignment question. So I shouldn't be giving out the solution. So I have given you I know this question is exactly a question, so I shouldn't be giving out the solution. I gave you the method to solve it. The rest, you should solve it, and then you can submit your assignment, and then it will be graded, and you can see. So yeah, as much as I'm not allowed to give out the assignment solution itself. So that's my limitation. But yeah, I gave you the idea, gave you the approach, and then the mathematics you'll have to do. Okay. What else? Let me. Okay, this mathematical problem is also there. One second. Again, a similar signal processing type question that let's say there is 64 QAM 64 QAM modulation is used, right? And for 4G, yeah, you can go up to 64 QAM, and your data rate is let's say 2 Mbps, 2 Mbps, right? And data rate is 2 Mbps, and you assume Nyquist rate pulse shaping. You are asked what is the time duration of each symbol. That is, how much time is needed to transmit one symbol, 164 constant. That is the question. So first things first, 64 form means 64 is equal to 2 to the power 6, right? So this is 6 bits. 6 bits per symbol. That is the relation scheme. Symbol, right? And so, and the data rate, which is R, that is equal to 2 Mbps, right? Actually, let's make it 12 Mbps. That will just make the calculation easier. 12 Mbps. And so, for to get time duration, so this is, let's denote it as TS. TS, time duration for each symbol is 1 by Fs, right? Where Fs is symbol frequency. Symbol frequency is nothing but bit rate divided by number of bits per symbol. Does this make sense? Because if I'm transmitting at a certain rate, let's say some Mbps rate, and I know I'm having like a certain number of bits per symbol, then yeah, Mr. Singer, so we can call it sampling frequency also. It's the same sampling frequency as well. Yeah, it's the same thing. The frequency at which we are sampling, right, is, and in each sample is one symbol. Each sample is one symbol, and so if we divide the bit rate by the number of bits that we are tracking in each symbol, then we'll get the symbol rate or the sampling frequency. I mean, in some problems it will be called as symbol rate. That's all. The same thing. And so this will be 12 divided by 6. So this will be 2 mega symbols per second. So see the units, it's 12 Mbps divided by 6 bits per symbol. So bits and bits cancel out. And so you have 2 mega symbols per second. And so the sampling time period will be 1 divided by 2 mega symbols per second. So 1 by 2 mega stands for 10 to the power 6, if I'm not wrong. Second, so this will be 500 nanosecond, I believe, or 0.5 microsecond. That is easy. That's the symbol duration, something like that. Again, simple idea. Any questions? There will also be many theoretical questions in all of the assignments, and unless you have doubts, I will maybe not stress on those, because those questions will essentially require you to study the slides and reproduce information there. So it's, and if there is some doubt, if there is something that you want me to clarify, I'll do it. Otherwise, I'll try to solve more conceptual problems. So that is it. So Ravi, okay, question 12 of the assignment, you mean? Let's see. This is a question about GSM, right? I'll index the question. This is the GSM question, right? Okay. That's what I have with me. Could you clarify what this question was? It's based on GSM. I assume so. One second. Just give me a minute. I will just to be sure if I'm doing it right. For this question I refer to the lecture notes.
Sir, in the previous problem, sampling frequency is equal to bit rate by number of bits per symbol. This
Yeah.
number of bits per symbol is 6, but we are not using 6.
Yeah. I mean, I did use 6, right? So bit rate is 12, and number of bits per symbol is 6.
Okay.
So 12 by 6 is 2.
Okay, thank you.
Right?
Thank you,
yeah.
sir.
Yeah, I just jumped a step, but yeah, I use it. Okay, anyway, I'll just explain this GSM problem. So for GSM, the discussion is there in the lecture, and so there is a calculation that shows that like the GSM data rate is like the rate at which the entire GSM frame is sent is 270.833 kbps, something like this. But then there are a lot of preamble bits and things like that. And so the effective data rate is actually the effective data rate, as in the data rate of the actual symbols being, the actual data being sent, is 22.8 kbps, right? And so the question, or you will get similar questions in normal GSM, 114 data bits are used in a frame. So this is normal standard GSM. Let's say we're given some non-standard implementation where you are said that, okay, you can convert maybe like you have let's say some two extra data bits, something like that. 2 extra bits you can allot for data. You are allowed this, right? So then, very simply, so you have 2 extra bits, and so now you have in this new GSM scheme, you have 116 data bits, right? So very naturally, if you think about it, if 114 data bits gives you 22.8 kbps, you can simply apply something like unitary method, basic mathematics, that instead of 114, if you have 116 bits, what will be the data rate? Because you'll be sending 2 extra bits per frame. So this will be 22.8 into 116 divided by 114. whatever be the value. Right? Similarly, you can solve. So its basic concept is you can just think of it in unitary method, right? Because all of the other factors, the data rate calculation 22.8 is 114 symbols divided by a certain symbol duration. Say something like 576.92 microseconds. So it's 10 to the power minus 6. Then you have a certain coding rate and yeah, modulation scheme coding rate, some kind of parity bits are there. So all of these things are accounted for, and so that brings down the rate. So instead of this number 114 here, if you have 116 here, so this answer you know is 22.8. Instead of 114, if you have 116, you can just multiply it by 116 divided by 114 and you will get your answer. I'm not doing the calculation, so you can just do it. So this simple application of unitary method. That's all. Is this clear? Okay. Thank you. Then fine. Okay, another type of problem that is there is regarding power consumption. Right? Power consumption. So I'll bring the example in the assignments and bring it to 5G for now. So let's say you have a UAV, right? A drone UAV. We are UAV communications. We are looking at UAV communication instead of normal cell phone. We have a drone which is fitted with antennas and behaves like a device, like a communication device. Doesn't matter, and just the concept is still the same. Drones usually fly with a limited amount of battery backup, right? So let's say there is some 21,000 milliampere hour, 21,000 mAh battery is there, right? And it is flying. And so normally during normal flight, power consumption is something like 1,000 milliamps per hour, right? That is normal flight power consumption. And stationary, so standstill power consumption is, let's say, 500 milliamps per hour, right? So if the drone is standing still, it will, for an hour, it will be consuming this. And let's say we are told that the drone always flies, let's say, flies for 30 minutes, rest, stand still for 10 minutes. So that is the pattern. Right? That is the pattern which repeats. So I have to find out how long. I have to find out time of flight of the drone. So how long will the drone be able to stay up in air? Something like that. So this is very simple problem if you think about it. That I have a certain battery capacity and I am spending energy. So at some point it has to end and the drone will not be able to fly. So I have to find out, I have to do the calculation. So calculation is very simple. I just cooked up the numbers, so I might not complete the calculation for you. But the idea here is to find out so the battery capacity C is 21,000 milliampere hour, right? So this is current. So if you see milliampere is unit of current, hour is unit of time, right? And so I want to find out per hour or per minute. Let me convert this into milliampere minute. So this will be 21,000 divided by, oh, sorry, 21,000 into 60 milliampere minute, let's say. Something like that. Actually, let me just, as you can see, I'm just making numbers up. So this is 200, this is 100, 20. Let me make it milliamperes per minute, right? Per minute. So 20 milliamperes per minute, 10 milliamperes per minute. Right. And so, what is the total power expenditure in average power expenditure in 1 minute? Average power expenditure in 1 minute. So we know that this drone will fly for 30 minutes. So the power consumption is 20 times 30 minutes, and it will stand still for 10 minutes. So 10 milliamperes per minute times 10 minutes. And if I divide it by the total duration of time, which is 30 plus 10, 40, then I'll get the average power expended in 1 minute, right? So you can do the calculation. I think it comes to be how much? 600, 700 by 40. Not even 70 by 4. 70 by 4 is 35 by 2, I guess 17.5. Average power expended in, so this will be, unit will be milliampere per minute. Sorry, 17.5 milliampere actually, right? Because this is milliampere, milliampere per minute. Right? So, so this is the average power expended in 1 minute. And so I can find out the total time of flight, which is time equal to capacity. So I have this much milliampere minute capacity, and for 1 minute, this for 1 minute, the amount of power expended is 17.5 milliampere for 1 minute. And so I can cancel out units and I can do the calculation, and I'll get the time of flight here in minutes. And we can convert it into hours or seconds or whatever unit is convenient. So this is some kind of idea that I wanted to give, that for any device that has a battery capacity, we need to take account of that also. And so we need to, if we know the battery capacity and we know the rate at which the energy is draining in the procedure for communication, we need to figure out the time for which the battery will last, right? Is this somewhat clear? Okay. Right. What else? Okay, so now we can come to more communication things. Again, a little bit of power consumption in communications. So I have been told that for some application, for some user, at the receiver, I need minimum SNR equal to 5 dB at receiver for the signal to be detected correctly, right? Then, so this is 5 dB at receiver at, let's say, 27 degrees Celsius room temperature, and noise figure, I think the notation is used, but I'll just write it here. Noise figure is given to be 9 dB, right? And bandwidth as is typical for LTE and many 5G cases, it's, especially 5G, it's 20 megahertz. LTE advanced for 5G FR1, 20 megahertz bandwidth. And so I have to compute what is the this thing, receiver sensitivity, which is what is the lowest value, absolute value of a signal that can be detected by the receiver. So how do we compute this? So the first thing that we compute is the noise floor, right? So we have the Boltzmann formula, 10 log 10 Boltzmann constant times temperature times bandwidth. So the value of Boltzmann constant, you can just find it online. It's 1.38 into 10 to the power minus 23 joules per Kelvin. And temperature is known to be, temperature should be given in Kelvin. So 27 degrees centigrade, we know is 300 Kelvin, right? T plus 273. And then this value is provided to us as 20 megahertz. So you can plug this all in and get the value of the noise floor to be somewhat. So this is calculated in dB. And so this is somewhat like minus 130.8 dB. dB watt? Because the units here are joule per hertz, joule 10 hertz. So it is watt, and so dB of watt is dB watt. This is like if you convert watt to dB. And so now receiver sensitivity equal to firstly you have to you have to take the noise floor, or it's called true noise floor sometimes, TNF. So you have to add the TNF plus the noise figure, which is denoted as F, because you need, this is by design, that you need your signal to be a certain margin above the noise level. And then you also have a certain minimum SINR requirement, which is mentioned as min SNR. So min SNR. So all of this add up, right? And so what you we'll get the answer as minus 130.8 plus 9 plus 5. So this will come out to be how much? Minus 130.8 plus 14 dB watt. So this will be 20 minus 116.8 dB watt, I believe. So this is the receiver sensitivity. So that is the formula for receiver sensitivity. So this is the minimum absolute value of in dB of the signal, so that the receiver can detect it. Okay. Any questions regarding this? Okay, so I've been asked about dBm value, dB and dBm, that conversion. So it's a very simple conversion. So what is the dBm value? Like dB, how do we define dBw? dBw is 10 times log 10 of 1 watt. And so dBm is 10 times log 10 of 1 milliwatt, right? And so, like, so what is 1 watt? 1 watt is 10 times log 10 of 10 to the power 3 times 1 milliwatt, right? Which is 30 plus 10 times log 10 of 1 milliwatt. Or 30 plus actually the value of a dBm, right? So actually no, it's probably like the wrong way. So so as you can see that the dBm is a smaller unit, right? dBm is a smaller unit, and so or let's explain it this way. This can get confusing, right? Let's say you know the actual value of the signal, something like P watts, right? P watts. And so the dB watt, in dB watt, it will be 10 log 10 P dB watt, right? And the same P watt is also 1000 times P milliwatt. And so in dBm, these two quantities are equal, P watt and 1000 times milliwatt. So in dBm, this will be 10 times log 10 1000 P dB milliwatt or dBm. And so if I expand this, this will be 30 plus log 10, 30 plus 30 plus 10 times log 10 P. So this is nothing but the dB watt value. So essentially, what you need to do is once you have dB watt value, you just add 30 and you get the dBm value. So this will come out to be minus 86.8 dBm. That's all. It's just plus 30 addition that you need to do. And then you get dBm value. Is this clear? I just kind of try to derive it for you. That yeah, it's just the base unit that is different. So mathematically speaking, dB watt is nothing but 10 log times P divided by 1 watt, where your base unit is 1 watt, and dBm is 10 times log 10 power divided by base unit of 1 milliwatt. That is why this difference comes, that there is a plus 30 factor plus 30 addition that you need to do to convert from dBW to dBm. So that is all. Is this clear? Okay. If this is clear, then that's it for today from my end. The other questions, as I said, are like it's mostly theoretical topics, and we should go through the lecture and try to solve it. I've tried to address most of the conceptual problems that can be solved in this chapter. Okay, the question is dBm greater than dB what? No. No. dBm is not greater than dB1. Let me use another example, right? Let's say length. We can write 100 centimeter is equal to 1 meter, right? 100 centimeter equal to 1 meter. Does this make centimeter greater than meter? No, right? Because we know 1 meter is longer than 1 centimeter. It's 100 times longer. So similarly, we have this thing, dBm, dBm, like dBm is like, if I have to simply write a conversion formula, dB watt plus 30, that doesn't make dBm greater. Actually, dBm is smaller, which is why it has a higher value, somewhat similar to 100 centimeter and 1 meter, right? Centimeter is a smaller unit, which is why it is a higher value. Which book? I think on the NPTEL website itself, Professor David Koelpillai's notes are available, and some versions of the book are also available. Some versions of the book in various languages is also available, so you can go through them. It's all there on the NPTEL website. I will like these notes that I've written, I will convert to PDF and share on Drive link, and the Drive link you will get from NPTEL office. It will be shared to you. So yeah, that you will get.
Okay.
For book, yeah, and for this question, minus 86.8 dBm is more than minus 116.8 dB watt. No, they are equal, right? It is just two different units. Like 100 centimeter is equal to 1 meter, right? They are the same thing. Just two different units. So, okay. Okay. Any other questions? If not, I can end this session early. I'm not seeing anybody new joining. So, okay, great. I'll end this. Thanks, everyone. As I mentioned, the YouTube recording and notes, everything will be made available. Bye.